Okay, we get started here. Just before, I wanted to talk a little bit about the final exam formula sheet. Somebody had sent me an email asking to get that sooner than later, so that you could have that on hand. And then while I was doing that, I was using math picks. I just wanted to show you this thing is highly useful. Let's just go like this. Well, racing doesn't work well. This is not a true statement. There. See that? Oh, I can't draw it. But you see, I can't enlarge it, but you see above my writing, you see the formula being rendered. Not only that, now there's just the next step is to press the little button. Here, let me just see if I can manage to remember how to do this. I just started using this thing all the time. Done. Go like that. And then you're in here and you just ask it to produce the LaTeX and then you copy that into your document and you're done, right? So no spending sometimes going $sign, \sign, bracket, X, this and that, right? Math pick. Like you get to do this for free, I don't know, 25 times a month or something like that. And then if you're me and you realize that it's worth almost any amount of money to save hours and hours of typing, you pay like $6.99 a month and you can do as many as you want. You can also take an entire document. Like I'm doing some work requiring me to read some of the work of Poincaré, which is written in French, and it's written from like 1890 or something like that. I don't read French very well, and there's a whole bunch of math in it. So what I've been doing is I take a scanned document, I put it into MathPick, it does the optical character recognition, it translates all the math into LaTeX, and so it produces me a PDF with the French in there and all the math in LaTeX. And then I can simply put the French into Google Translate and put it back. And within like 20 minutes, I can take a paper and translate it from French into English and have all the math typeset in there. Sometimes you have to make little corrections based on like, poor quality scan or, unusual symbols they used in late 19th century French that it screws up on, but it is actually surprisingly good. Okay. In fact, you see this right here, the question from the quiz. I wanted to put that on the quiz, so I just took a picture of it in the textbook, and then I just imported the snip in, asked for the LaTeX, and put that into the quiz. I did not type it in myself. Okay, I just wanted to make you aware of that. And I started doing this because you'll see I put the Legendre polynomials on the formula sheet. So here is the formula sheet from the midterm, right? That's what we had in the midterm up until the operation order from the Gaussian elimination. And then to that, I have added the forward difference formula. I'm not going to ask for a centered or backward one. I added the cubic spline, boundary conditions, the natural clamped and not a knot boundary conditions. I added the order, the error bounds for the trapezoidal midpoint and Simpson's rule. I added the definition of the Legendre polynomials so that you can compute them should you need to, which you will probably not need to, but that makes you happy because you don't have to think, oh, what if I have to know those things? No, probably I will either tell you it, like P1, P2, and P3 are these guys, or if that fails, there's a method for computing them. The Lipschitz condition and the Euler method to which I'll add the error bound. What else do you want on this thing? That's what I want to know. Huh? It doesn't matter to me, really, in some sense. I mean, there's some things I won't put on, but I mean, I'm willing to add some more stuff. I'm just not fully sure what it is you want. Anybody got ideas about what they like? Besides what's here? All right. Failing to get any addition, what I might do is I may well myself add a couple more things as I'm writing up the exam, and as I we have a couple of things we haven't done, so you wouldn't know about that, right? To put on here. And then what I'll do, maybe even today, if I can manage to remember, I will just email this to you guys or send an announcement saying, if you want to reply, maybe I don't want to make emails, so I'm gonna put in the Canvas discussion. So discussion formula sheet for final exam. I'm gonna post this. You can reply to that discussion in Canvas, and if you want some stuff added, put it in there, and then I can update it. Yep. The Richardson. The Romberg? Well, Richardson extrapolation is the general procedure, and then Romberg integration is when you apply that to extrapolate. Okay, so I understand. I think I understand your request, but let me just and I will do it, in fact. But I think it's a bad idea for this reason. Can you see that? Yes, you can. Okay. Let me just tell you the reason why. So here's the Richardson extrapolation situation. You're trying to estimate something. You make some sort of N1 of H estimate, and then that has some type of error associated with it. And there's several possibilities for that. The most basic one looks like this. And then you can use that, and you can be told, for example, make an H/2 approximation to try again. And so you put in H/2 like that. Like that. Okay. And then you figure out by what you're looking at these two things, let's label these 1 and 2. The goal would be to get rid of the first of these things. So then you'd go, oh, in this case, I need to multiply this guy by 2 and then subtract, right? Okay, now I can put the little formula for that on there. The problem with that is it is possible, say, for example, that M looks like this. And the thing you're trying to approximate is you approximate it by some first approximate, and then it looks like this. Okay. And then that little formula that you're asking for will look different, right? And then okay, so the formula that is there, I believe they have the one when it looks like this, and you do this. And then it's also possible it looks like this, but then you do this, like we did on the quiz, or then you do this. And the formula is going to be different in each case, right? Or it looks like this. So here you could then go from here to the next one. You could be going H/2, H/3, whatever, H/17. I don't know, right? You can do what you want, or it could look like this. Let's see. We haven't even right. That one's not even in the textbook. But the idea is always the same. The idea is you take something that you want to know that you can't figure out exactly. You get some sort of approximation. You observe what the remaining terms look like. If they have this kind of nicely structure, then you can make some other similar type of approximation with a different step size. Combine those two things intelligently in order to eliminate this guy. It's always the same. If you want I don't really more likely on the final exam. If they do a hunter, last year. Consider trying to approximate that. And this is what the error thing looks like. And you're able to make the next step dividing by 4. What should I work to the next thing? Then that formula is not useful. So I think we should just perhaps just leave it off, right? Yeah. So and it should, for some weird reason, there's some Richardson extrapolation where you had to get to like N8P, right? And you need the formula because it takes too long. Then I will put it on. I will put it on either on the formula or either right in the question. Yep. There's no reason, no things. Asking is also fun. The other thing, let me just say along that same line is, for example, we had the Gaussian quadrature, which looked like this, right? And we're going to approximate that. And we have choices on how to do that. And we have, if we're going to do two function evaluations, our choice looks like this. Okay. That's not Gaussian quadrature yet. This is just saying I want to make some approximation for this integral. And I'm going to approximate it using two function evaluations. And I'm going to weight them. Weight them however you want, right? That is okay. That is it. And then we ask, how do we figure out what the optimal choices are for these guys, right? And it did turn out in the case, it is the case, is that if you want to make the optimal choice like this, if it's two function evaluations, you want to use the Legendre polynomial of degree 2, which looks like it's root 3, 1 over root 3, right? Is it that? I don't even have it memorized. Is it that one? We're telling? That the Legendre polynomial of degree 2? You might have a constant out front, like 2 or something like that. Everybody have that? Three x squared minus 1? Oh, okay, that's equivalent here. Okay. The 3x squared minus 1 equals to 0. That is x squared minus 1/3 equals to 0. With the half. Oh, I got the half. Well, that isn't going to matter on the position of the zeros, right? The half just goes away, right? When you're finding the zero. So we found for the Gaussian quadrature that this would in fact be some constant times f of 1 over root 3, or some other constant f of minus 1 over root 3. Okay. That in this case, in fact, we have now moved into this interval. Okay, the point I'm trying to make is it's like here is a 4-choice quadrature rule. Right? We have 4 things we're allowed to choose in the set of program: C1, X1, C2, and X2. What is the best choice? That is actually the question. And so rather than say necessarily really focusing on the Legendre polynomials, because you can do this one without knowing that, I think it's better to also, the same way, understand what it is we're trying to do, because the kind of questions you can just easily ask is you're here like that. You're saying, well, imagine a quadrature rule where you have to do this. I don't know. Yeah. Imagine you're in a situation where you are trying to find this integral from -1 to 1, and you for some whatever reason you have a measurement of your function at -0.5, and you have a measurement of your function at 0, and you're allowed to make a third measurement. Where do you want? X3. X3 is clearly got to be between -1 and 1. And you're allowed to then pick these weights. What should you do? That is the same question. That is exactly the same question as this question. And then the answer here is not written by but in my view, this is also a much more likely kind of question, because it's like, do you understand how it is that we're picking these guys? It's the same, I'm bringing this is the same kind of question, I think, but for me, this is the same kind of question as what you're asking. It's like, should I memorize the Legendre polynomials or just use those no matter, if I see a question like this, I should just quickly use, oh, no, you should not, right? You should understand that they came up in this kind of a case, and you had all four choices. And if you were be making this estimate, and you were told you're allowed to use a degree, you have 6 choices, you would be up to use a degree 3 polynomial. Then and you're going to make the optimum choice, yeah, then you'd use the Legendre polynomial P3 of X, having learned that here. But there's a whole pile of other possibilities in this here. You just want to know how for y, for x, like I'm going to make this, I'm going to now do this integral, -1 to y, for 1 dx. I'm going to basically make f of x equal to y. And I'm going to make it exact. Now I'm going to make f of x. I'm going to do that for as many choices as I have. 1, 2, 3, 4. I'm going to look forward to the following up. Right, that is a better choice. I mean, I can remember something, but so this is a much better question from my perspective, because it says you understand what it is you're trying to do. It's trying to get the maximum precise quadrature rule when we're allowed to move the nodes. And maybe we're not allowed to move some of the nodes, so that constrains us, but won't be as good as if we're allowed to put all the nodes where we want it to. Yeah. Okay. That's fine. But let's look at this where I will send out that what I so far got. And then you can put discussion or what. Yep. Yeah. So okay. So that's a reasonable thing. So here, yeah. So here you're right. These are the error bounds for the one step. I'm not going to try that. Like, I'm more happy to put stuff on the formula sheet just so you guys don't waste time memorizing stuff, because some of the stuff you're asking, it's like I'm not going to. You know, I don't see the value of saying here's a formula and one of the numbers is just listed for the formula. Can you put the rest of them in and tell me what the other number is? Like, I don't see a lot of value in that kind of question outside the fact that they're happy situation or something. So I don't know what's hard to say. Okay. All right. So yeah, that's the kind of thing to add. Sure, we can add that. And whatever you guys put in the discussion, I will either add it or I will say, no, forget it. You should know that yourself. Or I will say, you know what, I'm not adding it and you're not going to just don't worry about it. Should I fail on this exercise? Like you're at the final exam and you're like, she said we wouldn't need this, and now I need this, and now now it's the whole thing has gone down the drain for me. If that happens, it is possible I can make a mistake like that. Then put up your hand. I will come over and say to you, and you'll say to me, I needed this formula and it's not here, and my life has ended as a result. Then I will say, you're wrong. You don't need that formula. You're not thinking of this the right way. Or I will say, you're right. I can't believe I did that. And I will add it on the overhead to the world thing. Either way, well, one way you'll be unhappy, but you'll know. And the other way, I will correct the mistake. So it's not a disaster if that happens too, right? Huh? That being said, there are some things you should know. Like I really don't want somebody to ask me what the Taylor series for EVX is. Like that, like either like sort of my you get with the program and know the 3 basic Taylor series that you're going to need to know, EVX, sin X, and cos X. Just know those ones, right? Not complicated. If you don't know that, then you yourself have to remember how to keep finding the Taylor series over and over again. I'm not putting that on the thing, right? But surely after you learn the Taylor series, do that for EVX 18 times, you're like, you know what? Let me just remember this one. Okay. Other questions or comments about this whole formula sheet situation? Okay, let's talk about some of the material here. Where are we at? We are here, higher order methods. Okay. What do? We have learned how to use Euler's method for a single differential equation of degree of order 1. That's what we did first. And then we said, hey, actually, we can get a system of these guys that are coupled. So it means coupled means, let me just, y1 prime depends on y1. That's the typical situation, but these are coupled because it also depends on y2, where we have a differential equation for y2 prime. So we can get a system of first order differential equations, and nothing goes bad in our world if we simply think to ourselves, oh, instead of just having a single equation with some with I guess basically two variables over here, then we're going to have a system of equations, and we're going to treat the whole thing just like we have in linear algebra. We're going to have it in vector form. So the things we're trying to find become a vector. The functions that determine how the derivatives depend on the independent variables and the variable themselves become a vector, and or in the such conditions become a vector, and everything works in the linear algebra model. That's it. Exactly the same thing to this situation. That's where we're at. We write it out in vector notation, and we just receive in that line. Okay. We can do it in practice. We had something here that we just wrote out. Okay, so let's go. We're here. We're going to apply Euler's method to a system of ODEs written in vector format. So we have a vector. Now this is a vector, and we have vector. It's exactly the same. This is actually just a notation situation. It's actually, it's not, don't be dismissive of this notation. It's surprising how often in the history of math, somebody's come up with a new way of just writing it down, the new notation, and suddenly the whole bunch of problems is solvable because you can see it properly in the new notation. Okay, so here we do it like that. So what happens then? Our Euler's method, we have our initial conditions, now also a vector, and then the update rule that we have is now we know where we are at time t equals 0, and we're asking where we are at time 5 plus 1, where we know I, that is where we are at time, not at time, where that would be for this one, at time 5. All these things in this vector, and this is the same thing on this vector. Here we go. So we have this thing, WI. This is our approximation, WI, the approximation. And that is approximately Y. All the same. The upside here is that when you're solving differential equations numerically, and you have a higher order system, means I would eventually have something like this. There's a differential equation. You will notice it doesn't just have the first derivative, it has the second derivative as well. So this is second derivative. And if I had a differential equation that looks like this, there's another one. That one is third order. Okay, and in this case, higher order means greater than one. Now we're gonna find out that if we have a second order or a third order, we can turn that into, let's just say second order. If we have a second order equation, differential equation we want to solve, we can turn that into a system of two first orders. We never have to do anything else besides the system. If we have a third order differential equation, we can turn that into a system of three first orders. We have a test. Good score. Okay, so we can turn the higher order ones into a system of first order. Okay, that's good, and we're doing it sort of together. So we're starting with the nth order one, and we're saying if we have a differential equation where we have the nth derivative, like you can just think of this as square or something like that, as a function of an independent variable, and then the function itself and all the derivatives 1 degree less than m, and we've got the initial conditions where we know the function value at time 0, and we know the first m minus 1 derivatives at time 0, then we can, that is a higher order differential equation, and we're going to be able to turn that into the system of first order one. Let's take an example here. Okay, here it is. 2 squared y double prime minus 3 y prime plus 4y. What order is this? Right? Yeah, how is it in six? Oh, second. Okay. Oh no, it's already breaking down badly. Okay, this is second order. Okay, second order. I think I listened to too much rock music when I was a kid. Okay. How many initial conditions will we have? 2. Second order, and we'll have initial condition at time 0, wherever it is, wherever the whole thing is. It doesn't have to be 0, but whatever it is that we're starting at. Time is starting, and then you'll have the other initial condition will be on the first derivative. We have a second order, and then we have a initial condition like that. 2 of them, one on the function value at time 0, and one at the derivative. Okay, it's the same idea. So we want to find the function. We want to find the function y. What is the independent variable? In this particular change here. We want to find the function y of t such that if we do this is like saying t squared times my second derivative minus 3t times my first derivative plus 4 times b is 0. 2 of them. That's 12. Now we want to find y of t. Right? This is a second order differential equation. 2 initial conditions. Okay, I'm just gonna, you don't have to know how to do this. I will just frame this. The answer is this. Okay, now you can check that if you want, right? And why don't you do that so you make sure that you're on the program and know what this is. That is the answer. That means if I take the first and second derivative of this guy, I plug it into this equation, do this computation, I will get the answer. No. We are not going to learn in this course. We got to go to math for that. Right? We're not going to know how to get there. But what we are going to do now is understand how, using a numerical method, we could find. We'll have y at 0, but we'll figure out how can we find y at say 0.01, y at 0.02, y at like that, and then we could plot those things to try to see what y at t looks like. We're going to have discrete positions along where we're going to understand what this is. That's our goal. Okay, so what we're going to do is convert to a system of ODEs. Okay. It's not complicated, but I don't know. It's not complicated. I'm trying my best, but I have to say that to do this. It's things up with the index and stuff like that. Okay, so we have some differential equation of the nth degree. Looks like this. It's some function of an independent variable, and then the function itself, it's first derivative, it's second derivative, all the way up. And that's what we have, entire order of things. We have our independent variable within some range that we care about the thing. We have the initial conditions at time 0, which is with the starting time. We have a bunch of initial conditions. Like that. All the way to the and initial conditions, order, differential equation. Okay, now what we're trying to do is get a system of equations that has the solution we're looking for. What are we trying to find? How can you tell me? What are we trying to find? What are we trying to find? Yep. Yep. Exactly. We want to, that's what we're trying to find. What function is I know what the test derivative is in terms of the function itself, and we want to find what function it is. So in order to convert this thing to a system, what we do is this. And the method is going to be the same every time. We take y1 of t, and we put that equal to u of t. Okay? That is what we're trying to find, right? Then we start taking derivatives. And we take the derivative with respect to t of this thing I just wrote out on both sides. So y2 of t is u prime. Y3 of 2 is going to be, I take the derivative again on both sides, it's going to be double counted. So keep going like that. Taking the derivative with respect to t the whole way down. Ym the whole way down. Okay. Then we notice. What did we notice? We noticed that y1 prime of 2 is y1 prime. So this is where you have to be a little bit cautious. Y1 prime is what? In terms of other y's and y. Yes, it's y2, exactly. Okay, let's think about this. Let's do one more, and then this is kind of a two-step that's easy to sort of forget exactly how to do this. Y2 of 2 is what? In terms of y. Y2, absolutely. Okay, so let's just make sure that in case somebody didn't observe it, I am taking y1 prime. Well, you can see it right here in some sense. I took the derivative here. This guy here is y1 prime. Relabel as y2. You take the derivative on both sides and down. So here, you can go down and part of the program. Okay. This guy right here, y prime of 2 is U M P. And that is, let me start with it. Okay. This step, let me just rewrite this step. I'm just eliminating this step here. Okay. Got something out here. Okay. Here I have M minus one equation. And if I add to it this guy over here, I have M equation. Right here, right here, I have M equation. Okay. Now I'm going to define that vector y is 2. It's going to look like this. Y1 is 2. Y2 is 2. Blah, blah, blah. Yn is 2. I'm going to define this guy here to be y2 is 2. Y3 is 2. All the way down, because these are the derivatives. But we're going to do an example. The general method. Okay, so we got the initial condition, we put the minus to the right. I'm claiming that these illustrations. This is the equivalent. We had an mth order IDP look like this, U M and T equals C and T that is all the way to U and this one. That's where we started. And now I'm saying what we thought is this. I find at 3 a vector equal to F this guy. So where it was then the dot, this one. That's how you do it. Let's do an example. We'll do an example of pendulum. We're getting so the idea is to take higher order to transform it into a system, a first order one, and now we can solve using our only method that we have so far, Euler's method, kind of crappy method, and then we're going to have some other better methods coming. But the idea of taking it from a higher order and putting it into a system of first order remains the same. We're possibly mercifully not going to worry so much about the. We took a little bit of time to understand when we can actually find a solution to these things on the basic first order ones. The existence, uniqueness, and well-chosedness is similar. And we're not covering them. If I give you a higher order differential equation, you can assume that it has a not going to give you one for this. Okay, we're going to assume higher order system. All right, so we're gonna start out here with the pendulum. like this. This is the pendulum. Spin the blade. Ball on the end and you pull it out like that. Certain angle theta, the pendulum having a length out. That's the length of the string here. We make those even with something, right? On a mass is stiff. These are things you do to find myself easier, right? And then we want to understand what the period of the pendulum is. Does anybody actually remember that formula from high school physics? No, I'm not joking. Somebody might. No? Not a single person is like, so I, yeah. Okay. Oh, okay, so yes, you have for me the differential equation, right? Yeah, so how do I find the period of pendulum? Does anybody remember that? Like forget about the differential thing. Nobody remembers how to find the period of pendulum. So if our iPhone stopped working, what is it going to find? So I found out that the period is 1 over the frequency. Okay. What's the frequency? Oh, oh yes, you're getting close. So this is he's what you did, right? We're making some headway. Yeah. There's somebody who remembers it or has had time to quickly look at their phone. I don't know either way. Is it memory? You're a physics major, but there's probably some other physics majors in there. Well, I don't either. Okay. All right. So the period of pendulum. Okay, hang on. Let me just ask you something as a physics major. I think it's lost totally over in high school, probably, right? And it's more accurate when theta is small, right? Right, that's ultra statement. And what is the topic? That's this out. That's right. It comes in because sine theta is approximately theta when theta is small. Really good. So nice job. Okay, so this coming in. Yeah, exactly. Because you make this approximation. Right? When this thing allows you to move to this. And this thing, look guys, what is the Taylor series for the sine function? This is one of the three that you're gonna know, right? Sine function, is it even or is it odd? It's odd. Let's use the odd one, shall we? Right? Now what do you do? You truncate on the first. And then this is of course true statement when x is really tiny, because when x is tiny, this side cube is really, really tiny, and all is well. Okay, so that allows you to get that your thing from high school. Meanwhile, there is the when you add this is the normal way information from the world comes to you. The angle, the second derivative of the angle, you do the like a free body diagram or how you use in physics, and you come out with this differential equation. Then you wish to solve for that angle as a function of time. So I want to be able to keep it, like, if pendulum starts from some initial angle, I want to get what angle is 153 seconds later, whatever. We have this differential equation, which is the gravitation of light. Okay. That's where we're at. We got this. We boiled down the physics problem. Homogeneous, which means it's zero over here. A homogeneous second order differential equation for which we wish to provide a numeric solution. That's what we're trying to do. We're going to get two initial conditions because we have a second order equation. We need two initial conditions. One's going to be telling us where is this thing at time zero and what is its initial velocity at time zero. So if we just someone out here, but you know where it is and you know how fast it's moving at time t is. And then you're like, where is it going to, what angle is this not going to be at some other time? Okay, so we're going to solve this guy using Euler's method. We may run out of time of doing this, so let's just start and then we'll see. We set up, it's a second degree equation. We had it written like this. That's how we had it written. So we see that we'll write it like this. We see that this second derivative depends on the function of theta. This is what we're trying to find, theta t. Doesn't actually depend on theta, it doesn't depend on theta phi. Okay, we set up the system of a curve looking like this. This is going to be theta t, this will be theta phi. Okay, following from that data. We set up the vector of the function. What is the first one going to be in this thing here? Well, it's going to be like y1 prime and y2. This is not what's going to be in there, y2 prime. So according to our data, this is a hint. What is y1 prime? Y2. And what is y2 prime? It is y3, but in this case, we're at the last step. Actually, we don't have a y3. Pardon? It's this. I'm sort of mixing a notation here. This is y1. Can we see this? Maybe not. Let's write it. But you know what we're gonna do? We're gonna stop right now. I think this is a good idea. We'll stop. So you guys can go back and look at the stuff on method, attempt it out on this day, and then we'll come back. And Wednesday we'll start again with this example. We'll go through. It'll move to the second example. How to go from the higher order one to the system of lower order one. I will see you on Wednesday, and I'll be over my office hours there at 2:30.